All right. So we're looking at the absolute value of p-Adics, considering like how continuity works in the reals, how it's alleged to work in the reals. Okay. So basically, the way your absolute value of a p-Adic works is you're taking the absolute value of some number with respect to your base, p, and they're called p-Adics because the p indicates that it's a prime, because when your base is prime, things work nicer. It's also true for real numbers. If your real number base is prime, some really nice things come about, but nobody wants to do that. They want to use the worst possible choice, base 10, whatever. It's like an anti-prime has nice properties, a prime has nice properties, but what we do is we find the worst, the exact middle, which is the absolute worst. Even like base 14 would be better because it has the same number of divisors as 10, but it's larger, so it more closely approximates a prime than 10 does. 9 would be better because it more closely approximates a prime. Only 3 goes into it. 11 would be better because it is prime. 8 would be better because it's closer to being an anti-prime. 7 would be better because it's prime. 6 would be better because it is an anti-prime. 5 would be better because it's prime, right? And we can go in the other direction. 12 would be better because it's anti-prime. 13 would be better because it's prime. 14 would be better because it has the same number of divisors, but it's larger, so it acts more like a prime. So literally 10 is like our worst choice, but it's what we use. Anyway. p-Adics, we use primes. Okay. It's preferable to use the primes. So we just indicate it that way. Okay. Now, the absolute value of a p-Adic value is 1 on k, where k is 1 multiplied by p, your base that you've chosen, the number of times that p divides into a. So, over here, we have this p-Adic calculator that I found. Quite nice. I appreciate that this exists. This is lovely. So, if we look at, let's see, down here, we're going to ignore, we're really just looking at this line right here. Right here. So, when a is 0, the absolute value is 0. Cool. Okay. When a is 1, absolute value is 1. Okay. Cool. 2 doesn't go into 1. 2 doesn't go into 0. But they behave differently, right? So 2 to the 0 power is 1. So, but 0, there's no correlation there, right? So you end up getting like a 1 over infinity or something. I'm actually not entirely sure how that comes about. It feels to me that this one is ad hoc. It's not properly defined. It's not included in this definition. I don't know how to get to it from this definition. So there's an incompleteness to this definition already. Anyway, okay, now we go to 2. And our absolute value is now 1/2. Because 2 goes into 2 once. So 2 to the first power is 2. So 1 over 2 is 1/2. Okay. Now, you might notice there's 1 0 here. If we go to 4, which is 2 squared, we get 2 zeros here in the binary expansion of 2. And our absolute value is 1/4. If we go to 8, that's 2 cubed. So there you go. Our absolute value is 1/8. Okay. This is in binary, so it's very, very simple. If we go to ternary or something, some more nuanced patterns arise. Okay. So, first off, as I previously noted, this concept of an absolute value is just fucking stupid. We don't need to wrap the number, because once you take the absolute value of it, you can't do addition and stuff with it anyway. So we can just mark it after the fact, right? So this is just an abbreviated notation that I'm going to use from here out. Okay. So, the one that this actually opens with when you load this, it loads with this one. Alright. Now, this one seems strange, right? So there's no ending 0. Okay. Fine. that means that its absolute value is bigger than a half. But the only value that's possible bigger than a half is 1. We have this huge gap between 1/2 and 1. This seems strange to me because there's a lot going on with this number. That should bring it down from 1 closer to a half. Well, not necessarily. It shouldn't necessarily be closer to 1/2 than it is to 1, but it should be closer to a half than 1 itself is. Okay. And we get this sort of sense from looking at the real numbers, right? When we take the absolute value of the real numbers, okay, so if we've got -1, its absolute value is 1. If we've got positive 1.1, its absolute value, it isn't 1, it's 1.1, right? If we've got negative 1.0001, its absolute value isn't 1, it's 1.0001, right? So, like, this detail out here gets preserved in the absolute values of real numbers, but in the absolute value of p-Adics, that detail is just thrown away. Because all we're interested in when we do this is how many zeros are there. That's it. So our exponent is literally just in the whatever our base is, expansion of this number. How many zeros are there from the ones place over? That's it. That's all we're considering. We're not considering anything else. Now, as a way, as like a very rough sense of how big the value is, fine. I have no problem with that. But I feel like you're throwing out important information, because generally what is occurring here as we go bigger, as we get larger and larger values with more zeros, what's happening is we're approaching something. That's the whole point of the p-Adics. Okay, this is all zeros. Right? So 1 with an infinite number of zeros is pretty much the limit that we're interested in here. That's basically going to have an absolute value of 0. It isn't, but it's exceedingly close, right? It's pretty much the limit of it. Okay. But this is an absolute value of 1. Just as this does. And this. This and this have the same absolute value. Really? Really? Those are the same? Those are the same size as each other. Are you sure? This one, I think you got right. This one versus this one doesn't look right to me, right? So it's like, okay, so the real numbers, what we're doing is we're looking at the expansion to the right. The p-Adics, we're looking at the expansion to the left. Okay. But, so the way that, if we analogized the way we're finding absolute values to the reals, if we analogize the p-Adic absolute value to the reals, what's going to happen is it's going to look like this, right? So you've got 0.004 absolute value. That would be 0.001. Okay, so the 4 gets thrown away. We just ignore it. But also, it doesn't matter what we put after it. It's still the same size. Here, with the p-Adics, it doesn't matter what you put before it. So, This 1 right here, it doesn't matter what comes before it. It doesn't matter what's over here at all. If it's just the 1, we get an absolute value of 1. If there's a whole bunch of 1s before it, it's still 1. If there's a whole bunch of 0s before it, it's still 1. It doesn't matter. It doesn't matter. I don't think this is right. This doesn't feel right to me. This feels like you're doing like a natural number version of the p-Adics. Like this is like the integers, the p-Adic integers is what you're finding. Which, insofar as it goes, if we were honest about that, that's fine. I don't have a problem with that. But that we don't say that that's what we're doing. We're like, oh, this is just the absolute value of it. It's like the absolute value of 2.5 is 2. Is it? Why? Shouldn't the absolute value of 2.5 be 2.5? Why is it 2? Well, because that's how we defined it. But your definition already doesn't work, because your definition doesn't explain 0. So you're not going off the definition. You're going off of something else. And you're not saying what that something else is. This is not rigor.